Hello class and welcome to the session. Let's study in detail about three-phase transformers in specific for your fourth semester DC machines and transformers subject. In this session, we're going to see what makes a three-phase transformer. Nothing much. It's just three single-phase transformers connected together. Condition is they need to be identical. These days, we manufacture them as one single unit. In a single core, we're going to have three different windings. We're going to look at it in the mathematical aspect to understand how it works and what's the math behind it. To understand this better, we need to look at the fundamentals. I will go review that for you and we'll also go through a simple problem. In this case, we're going to consider a 5 kVA transformer. A 5 kVA transformer, which is, we talked about kVA, it's not kilowatt, it's kVA. The reason is it's a transformer, it does not have a definition of load, so it does not have watt rating, since it does not have power factor. So it's kVA. So since it can estimate about 5000 watts in theory, in kVA considering unity power factor. Now let's look at what makes it up. It has a HV coil, a high voltage side, which is about 200 volt, and a low voltage coil side of 100 volts. And the turns ratio is 2, which is it can step up or step down, and it's twice. So it's 100 by 200 by 100, so it's 2. So the rated current of the HV coil is 5 kVA by 200, which is 25 amps. The rated current of the LV coil is 5000 by 100, which is called 50 amps. So what you need to understand here is, though it's 5 kVA, there's 5 kVA of power being transferred, kVA being transferred from the primary to the secondary. When it's high voltage, 200 volts, the current is 25 amps. When the voltage is reduced from 200 to 100, on the LV side, the current doubles. So when you're talking about a voltage transformer, if it's a step up transformer, the current would be step down. If it's a step down transformer on voltage, the current would be a step up. Transformation ratio, or the turns ratio, would remain the same. So if I have my primary as 200 volts and my secondary as 100 volts, my primary current would be 25 amps and my secondary current would be 50 amps. Hope this is clear. Let's look at it in a practical demonstration. In this case, I have my primary as star connected and my secondary delta connected. So my turns is, my primary to secondary is the number of turns making up each phase. So in this case, this 200 is 200 twice the number of turns compared to this voltage here, which is 100 single time, once the turn. So looking at this 100 volts to this 200 volt. So the number of turns ratio between the primary and secondary is this the configuration. Now we're considering the primary to be star connected and secondary to be delta connected. If I have a star connected primary, each phase voltage, there's something called a phase voltage, there's line voltage. So when I say a phase to phase, and I'm looking at phase to phase, the phase-to-phase voltage will be root 3 times the line voltage, which will be root 3 of 200, which will be 346.4 volt. In the secondary case, now the same thing happens for current here. Here, the current single phase current we saw based on the previous slide is 50 amps. Now this 50 amps is going through this line, plus these two coils also feed a current into this line. That will be root 3 times more. So that will be 86.6 amps. How is that? Root 3 into 50, 86.6. So the fundamental concepts is the principle of root 3. Reason being is 120 degree phase apart. That influences the way the current and voltages are split or combined in the circuit. Let's look at a similar configuration where the primary is delta connected and secondary is star connected. Now the primary current we see is 25 amps because based on our 5 kVA calculations. But here, looking at the current when you look at per phase on my input, it will be 43.3 amps, which is root 3 times 25. Similarly, on my secondary, I see 100 volts on my secondary, and root 3 times 100 would be 173.2, which is, if I measure the voltage between this line and this line on my secondary, or this line and this line on my secondary, it will be 173.2 volt. So this is a simple understanding of how voltages and currents are combined in a delta circuit. But when you look at this here, the 50 amps that's flowing here is the same thing that flows out on this particular line, and the 25 amps is the only thing that combines in the primary. Now we look at the previous one here, Here the 25 amps that flows through each phase is what flows through each coil set. But here the 50 amps that flows is not the one that comes out from between each line. Each line has 86.6 amps. So currents are combined, voltages are split. Or voltages are combined, currents are split. So that's the take home from this. Take your time, understand it, go through it in detail. Let's look at the fundamentals. What is three-phase power supply? It's three single-phase power supplies, three single-phase sine waves, 120 degrees apart. So when you look at the phasor diagram, you understand that when we have our three phases combined, the three phases are 120 degrees apart. So when you look at the three-phase circuit, why we use three-phase circuit is because when you have an X amount of, example, I have 5 kilowatts of power to be transmitted. If I have to have 5 kilowatts of power to be transmitted, it takes me much less copper to transmit it than having a single phase of 5 kilowatt. Reason being, I'm going to transmit it for high, especially talking about power transmission, you're talking about short distances, it's long distances. And we're not talking about low voltages like 100 to 200 volts, we're talking about thousands of volts. In that case, it's much more economical to have three-phase power than to have some single-phase power for a given amount of power to be transmitted. It's not exactly 180 degrees apart, it's 120 degrees apart, and that's the difference of how we save on power. Now, understanding the exterior of the transformer is different. On the right side you see it. On the interiors, I have my three voltage coils of primary and secondary. The turns ratios, yes, differ. Now I can have it configured either as a star configuration or a delta configuration. Example, if I connect all these first ends together and I take these three different ends away, it'll be called a star connection. Or if I take this end and this end connected together, this end and this end and connected together, and this end and this end and connected together, it will be a delta connection on my secondary. So it's all about how you configure it. How do you connect it together? You're talking about phase voltages, line voltages, and what voltage are you requiring, and what currents are you requiring, and what efficiency you're going to be working at. How much power you're going to be transmitting, how many lines of wires or conductors do you require. When I talk about delta connection, I need 3 wires. When I have star connection, I have 4 wires. When I generate power to balance it, I have the 4th wire. When I want to transmit over a long distance, I convert it into a delta connection, step it up the voltage really high, thousands of volts, transmit it to the destination, and make it back into single phase power. Let's look at that. So my destination is going to be a star connection. In my transmission is going to be delta connection, similar to this diagram. So my delta connection is transmitting the power. When it comes to my transformer that is in my distribution center, the primary is delta connection, may be 11 kV, and the secondary should be 440 volt. So that 440 is what we're going to look at. So my secondary is going to be 440 volts. So it's going to be 230 volts per phase. So if I'm going to connect my load between a phase and a neutral, I would get 230 volt. If I'm going to connect the load between phase and a phase, I would get 440 volts. So I'd be able to get voltages from 230 to 440 depending on how I connect it, or I can have a 3-phase load connecting between phase 1, L1, L2, and L3. Not L2, it's L3. So connecting all 3 different phases, I can have a 3-phase load. Might be a 3-phase motor running the elevator shaft. Such loads require 3-phase power, and that 3-phase power is taken directly from phase 1, phase 2, and phase 3 on my secondary. So this is the basics of how 3-phase transformers come about and what are the calculations behind it. It's simple calculations, don't get confused. We talked about how we could calculate the rated currents of the coils, kVA by the voltage, we get current, and we talked about how we could calculate the root 3 times voltage ratio and current ratio depending on what is combining. In this case, the current is the same. This is 200 volt 25 amps, 200 volt 25 amps, but when it comes to secondary, it becomes 50 amps. Those 50 amps combined between the other 2 phases, you get 86.6 amps per baseline on my secondary. So this is the basic calculation for three-phase transformers. Understand it. If you have any questions, drop me a message and we'll do a lot more calculations offline if that's required. Okay, and that will be it for now, and we'll follow back on our Google Classroom session. I will send you the messages or notes required on the Classroom page. Please follow up on the page and drop in your messages, and we will interact right there. Thank you for your time and have a great day.